Hi everyone. So today I'll be talking about my lab tree on using graph neural networks for fraud detection. I applied graph neural networks on a Bitcoin transaction network to identify suspicious activities. So the problem overview is fraud detection is very important in financial systems. Traditional machine learning treats transactions independently and ignores relationships, but fraud usually happens through connected patterns and not isolated events. So it makes more sense to model transactions as a graph, and that's why graph-based learning is more suitable here. And graph neural networks are useful because they model relationships between entities using nodes and edges. They also capture how neighboring nodes influence each other. This is important in fraud detection, where one transaction can affect others. So, GNNs are well suited for things like transaction networks, fraud rings, and money laundering patterns. I used the Elliptic Bitcoin Transaction Dataset. It originally has around 200,000 transactions, each with 165 features and connections between them. And each node is labeled as legitimate, fraud, or unknown. After pre-processing, I removed the unknown class and converted it into a binary classification problem. So finally, I worked with about 46,000 nodes. And this is the model architecture. I used a two-layer graph convolutional network, or a GCN. So GCN works by updating each node's features based on its neighbors in the graph. That happens in, like, normally that's how graph neural networks work. And instead of treating transactions independently, it allows the model to learn from connected transactions. So this is useful because fraud often happens in groups or patterns. And in each layer, the node aggregates information from its neighboring nodes and combines it with its own features. This process is called message passing. And after aggregation, the features are transformed using learnable weights. I use two layers so the model can capture information from both immediate neighbors and neighbors of neighbors. The hidden dimension was varied between 32 and 64 to test model capacity. I used ReLU as the activation function to introduce non-linearity, and dropout was added to reduce overfitting and improve generalization. And overall, this is a simple architecture, but it effectively captures both node features and graph structure. Then this is the hyperparameter experiments, and I experimented with different hyperparameters like hidden size, dropout, and learning rate. From the table, we can see how each change affects the performance. The best result came from the experiment 2 with lower dropout at 0.3. Increase in dropout too much reduced performance slightly. So overall, this shows that careful tuning improves the model. And now the training, validation, and test accuracies. So this plot shows how accuracy changes during training. All three curves improve steadily, which means the model is learning well. And the validation and test curves stay close to training, so overfitting is minimal, and the small gap between them indicates good generalization. Overall, the model is stable and performs consistently. And this is the confusion matrix. It shows how well the model predicts each class. Most normal transactions are correctly classified, as seen in the top left. Fraud cases are also detected well, but there are some misses. We have fewer false positives, which is good for real world use. And overall, the model performs strongly but can still improve on fraud detection. And this plot shows the node embeddings reduced to 2D using principal component analysis. Each point represents a transaction colored by its label. We can see some clustering, especially for the fraud class. And this means the model is learning meaningful representations. However, there is still some overlap, which explains misclassifications. And this is a small subgraph from the dataset showing how transactions are connected. Each node is a transaction and edges represent the flow between them. We can see clusters forming which may indicate related activities. Fraud often appears in such connected patterns rather than isolated points. And this structure is why graph-based methods are useful here. And to conclude, graph neural networks are effective for modeling relationships in transaction data. We achieved a high accuracy of ground around like 96.7 or something, yeah. So using graph structure clearly improves fraud detection performance, and the model also remained stable across different hyperparameter settings. So overall, this shows GNNs are a strong approach for this problem. Yeah, so that's all. Thank you.